Hello, and welcome to Linear Algebra. This is lecture 5, and our topic today is vector spaces. So last time, we talked about fields. So for example, the rationals form a field. They form a subfield of the real numbers, which in turn forms a subfield of the complex numbers. So remember, a field is a set together with two operations, addition and multiplication, and those two operations have to satisfy various properties like the existence of neutral elements, the existence of inverses. In the case of multiplication, that's for everybody except for 0, right? And there are two distinguished elements, 0 and 1, right, where 0 serves as the additive neutral element and 1 as the multiplicative neutral element. So these three fields we saw are just the usual way of doing arithmetic. And if you start with complex numbers, you stay within complex numbers. If you start with real numbers, you stay within real numbers. If you start with rational numbers, you stay within rational numbers. But we saw that there are other fields. So we saw, as an example, f sub p for p prime, especially the case f sub 2. So f sub 2, you just have the two distinguished elements, 0 and 1. But you can give that set two operations so that you get a field. So that's what we saw last time. This time, we're going to talk about vector spaces. So for example, we're going to talk about how Rn is a vector space over R, right? So basically, a vector space is going to have scalars. The scalars are a field. So now that we've talked about field, we're going to talk about the vector spaces over those fields. So Rn is a vector space over R, and for any field, Fn is a vector space over F. Okay, so first let me say, so you know what to expect, like a field, a vector space is a set with two operations. But here, those are vector addition and scalar multiplication. Okay, so just like for a field, we're going to give a formal definition, which means we're going to say what properties these two operations have. Right? Also, just like a field, there's going to be a distinguished element. In this case, it's going to be the 0 vector. Every vector space has a 0 vector. Okay, so here we go. A vector space V over a field F is a set with those two operations, right? So vector addition, scalar multiplication, and a distinguished element, zero. So this is known as the 0 vector. Such that, okay, so here are the properties we're going to demand from vector addition and scalar multiplication. So let's start with vector addition. So first, of course, V is closed under vector addition, right? Which just means that if I give you two vectors in V and you add them together, you get another vector in V, right? Which also, okay, so here are the properties of vector addition. It is associative. right? So remember, this means that if I give you 3 vectors and you want to form the sum of all 3, right? Well, you could go about this in 2 ways and you're going to get the same answer. You could first sum v2, v3, and then add v1 to that on the left, or you could first sum v1, v2, and then add that on the left, v3. Right? This is also commutative, so you don't have to worry about whether you're adding on the left or the right. If you have any 2 vectors, then v1 plus v2 is the same as v2 plus v1. This has a neutral element, right? As we mentioned above, 0 serves as a neutral element, which means if you do 0 plus v, you get v for any vector v in the vector space. And it has inverses, so this additive inverses for vector addition. So that is to say that for every vector v in the vector space, there is another vector which we denote minus v, such that v plus minus v is equal to the 0 vector. Okay, so that's it for vector addition. Then we also have scalar multiplication, so we're going to say this is closed under scalar multiplication. As usual, closed just means that doing the operation doesn't leave the set. So in this case, we're going to say that if you give me any vector and you pick any element of the field, then you can multiply them together, a times v, and you get another vector. Okay? Which also, okay, so for scalar multiplication, we're going to get that it is associative. Okay, so how associative looks like here is you pick 2 elements of the field, a and b, and then 1 vector v, and then you're going to multiply them together, right? So what's ambiguous here is that it could be that you first do scalar multiplication with b, and then do scalar multiplication with a, or that you take the product of a and b in the field, and then do scalar multiplication by that, right? And associativity is that it doesn't matter which way you do it, you get the same vector. And we also ask that this has a neutral element. Right, so the scalar, right, so remember every field has a multiplicative neutral element. So that same scalar satisfies that 1 times v is equal to v for every vector in the vector space. Okay, so those are the properties that each of these operations have by themselves. And then finally, we want to talk about how the operations play together. And as in the case of a field, in this case, what we want is for one to distribute over the other. So vector addition and scalar multiplication distribute over each other. What I mean by that is that if you do a times v plus w, then you get a times v plus a times w. This is for every element a of the field and vectors v, w. And if you were to do add together a and b inside the field and then do scalar multiplication against a vector v, that's the same as if you first do scalar multiplication with a and with b and then add them together. Okay, So that's the definition of a vector space. Again, it's just like the definition of a field. We have a set with some operations and a distinguished element, and then just those properties those operations are required to have. Okay, so let's look at some examples. First, just like we have Rn over the real numbers, we have Fn over any field F. So for any field F, Fn, so Fn is just a set of, we're going to write them as columns with entries A1 through AN such that each AI is an element of the field. So this is a vector space over the field F with vector addition given by, okay, so let's say that you have the vector U has entries A1 through AN, and the vector V has entries B1 through Bn. Then the vector U plus V is the vector whose entries are A1 plus B1 dot 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 AN plus Bn. And scalar multiplication given by, okay, if you give me an element of the field and you give me a vector, say with entries B1 through Bn, then A times V is just do scalar multiplication in each entry. So it has entries AB1 dot 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 ABN. Okay, so I will let you check that the properties of addition and multiplication in the field carry over to make Fn a vector space. So it means that the operations of vector addition and scalar multiplication, as defined right here, satisfy all of the properties of the definition. Okay. Another thing I want to mention is that the linear combinations and the span of vectors that we've talked about for Rn carries over for arbitrary vector spaces. So given vectors, V1 through Vk in a vector space V over F, a linear combination is a vector of the form C1 V1 plus dot 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 plus CK Vk with the CIs, these coefficients, elements of the field for all I. So just like we talked about for when we're working with vectors in Rn, linear combinations are just all of those vectors you can form from a given set of vectors by using the two operations in a vector space, by using vector addition and scalar multiplication, right? So I give you these k vectors to start with, and then these are the vectors that you can form using those, right? And the span of this set of vectors is denoted with these triangular brackets. It's just a set of all the linear combinations. So sum I goes from 1 to k of Ci Vi, such that the Ci are elements of the field for every I. So this is the set of all possible linear combinations. Okay. Now, it's easy to see that the span of a set of vectors is itself a vector space. So it's going to be a vector space over the same field with the same operations as V, right? So if I give you two elements of the span, so that's just two vectors in V that look like this with different coefficients, then you already know how to add them. You know how to add them because you know how to add any two vectors in the vector space V. And then when you add them together, if you add two linear combinations, then because of the distributive property of scalar multiplication with vector addition, the sum of two linear combinations is another linear combination. So we see that the span is closed under vector addition. Also, it's true that if I give you a linear combination and then a scalar, you can multiply this vector by that scalar, and you will again get a linear combination, right? All that happens is that that scalar multiplies each of these coefficients, right? So that shows that it's closed under the same operations, and you can check, I'll let you check, that all of the properties in the definition of vector space are satisfied by those operations on the span of these vectors. Whenever that happens, whenever we have a subset that of a vector space that is itself a vector space with the same operations, then we call it a subspace. So in this case, we say that it is a subspace of V. Okay, now actually when you want to check that something is a subspace, you don't have to check every single part of that definition, because parts of it you get for free because you've already checked that for the vector space V itself. So let's write this down. So notice that if we want to check if U subset of V is a subspace, right? So we have a subset of a vector space, and we want to know if it's a subspace. Then, since we already know that vector addition and scalar multiplication are well behaved in V, we just need to check that they, let's say, respect U. Right? So concretely, U is a subspace if and only if, okay, so we need to keep the distinguished element, right? So we need to know that the zero vector is inside the subset. We need to know that if you give me an element of the subset, then the additive inverse is inside that subset. And then we need to know that if you give me two elements of the subset, then the vector addition stays inside the subset, right? Which we would say that it is closed under vector addition. And similarly, we need to check that if you give me a vector inside the subset and you pick an arbitrary element of the field, then the product is inside that subset, right? And so this we would say that the subset is closed under scalar multiplication. Okay, so that's all we need to check to know that a subset is a subspace. Okay, so let's do an example. This is a very important example. Since, as I've mentioned, most of this course relates to solving systems of linear equations, right? So let's let S inside f to the n be the set of solutions of a homogeneous system of linear equations. Over f, say with n variables, right? So this n is the same as this n. Okay, so the system, remember a system of linear equations looks like this, where these coefficients a, 1, 1 through a, m, n are elements of the field. And then you have a right-hand side, and here I'm going to put all of the right-hand sides equal to 0. That's what homogeneous means. So here, homogeneous means that the right-hand side is 0. Okay, so let S be the set of solutions of a homogeneous system of linear equations over F. Then S is a subspace of Fn. Okay, so let's check this. Right, so indeed. Right, so as we just mentioned, we only need to check 4 things, right? We need to check that the 0 vector is an element of S, right? So, well, that's true, since if we put x1 equal to 0 up to xn equal to 0, so every variable here, we set it equal to 0, then the left-hand side is equal to the right-hand side, because 0 times anything gives you 0, and then 0 plus 0 gives you 0. So this is a solution. Okay, next we need to check that if u is a vector in S, then minus u is also a vector in S. Right? Okay, so this is true. It's true since, so let's say that u with entries u1 through un is in S, so that's the same as saying that x1 equal to u1 dot 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 xn equal to un is a solution. That's the same as saying that, so let's look at what happens in the ith row. ai1 u1 plus dot 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 plus ain un equal to 0. Right, so this is for every I. This is saying that the ith equation is satisfied. And then I can multiply this whole thing by minus, so I can put, well, if this is true, then I can move everything from the left-hand side to the right-hand side, right? And that's going to replace the vectors with their additive inverses. And so I'm going to get that AI1 times minus U1 plus dot 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 AIN times minus UN is equal to 0 for every I. And that says that x1 equal to minus U1 to xn equal to minus UN is a solution. Which is the same as saying that minus U is an S. Okay, so we've checked that we have the 0 vector. We've checked that if we have a vector, we also have its additive inverse. Next, we just need to check that it's closed under vector addition and closed under scalar multiplication. So, closed under vector addition. All right, so let's say that V, the vector V, so V with entries V1 through Vn, and the vector W, if this is an S, if both of these vectors are an S, then we know that AI1 V1 plus dot 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 plus AIN Vn is equal to 0 for every I, and AI1 W1 plus dot 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 plus AIN Wn is equal to 0 for every I. But now adding those together, we see that AI1 V1 plus dot 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 plus AIN Vn plus AI1 W1 plus dot 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 plus AIN Wn is equal to 0 for every I. Right, now I use that vector addition. No, this is not vector, these are scalars. The scalar addition is commutative to write this as AI1 V1 plus AI1 W1 dot 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 plus AIN Vn plus AIN Wn is equal to, okay, and then I'm gonna, so on the one hand, this is equal to 0. On the other hand, I can use the distributive property in the field to write this as AI1 V1 plus W1 plus dot 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 AIN Vn plus Wn. And then the fact that this is 0 for every I tells us that the vector V plus W, whose entries are V1 plus W1 dot 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 Vn plus Wn is an element of S. Okay, and then finally we just need to check closed under scalar multiplication. So let's say that we have a vector V with entries V1 through Vn inside S, and then we pick an arbitrary element of the field. We need to check that the scalar product is inside S, right? But this is the same as saying, well, the fact that V is in S is the same as saying that AI1 V1 plus, oh, okay, since we already have a bunch of A's, let's give this scalar a different name. Let's call it lambda. Plus AIN Vn is equal to 0 for every I. Now, if I multiply by lambda, then it's true that lambda times AI1 V1 plus dot 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 plus AIN Vn is equal to lambda times 0, right? But that's just 0. And this left-hand side I can write as using first the distributive property and then the associative property, all inside the field F. I can write this as lambda AI1 V1 plus dot 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 plus lambda AIN Vn. And since I get 0 for all I, that tells us that the vector A times V, lambda times V, which is lambda V1 dot 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 lambda Vn, this is an element of S. And that's what we needed to check. So we're done. The set of solutions to a homogeneous system is always a subspace. Okay, let's do another example. Okay, here's an important one. Let's call it, so we will use the symbols CAB. The C stands for continuous, and then AB is just the interval. So this stands for all continuous real valued functions defined on AB, the interval AB. So more symbolically, we would write this as a set of all those f that go from AB to real numbers, such that f is continuous. Okay, so CAB is a vector space over the real numbers with vector addition and scalar multiplication given by pointwise addition and scalar multiplication, well, and multiplication. So what's that mean? Well, that is, if you're given two functions, f and g, and they're both continuous functions on the interval AB, the function f plus g, right, defined on the interval AB, taking values in the real numbers, given by f plus g at the point x is just f of x plus g of x, right? This is continuous. Right, so that gives us an addition of two vectors. Here the vectors are functions from the set of continuous real valued functions on AB into the set continuous real valued functions on AB. And then for scalar multiplication, we're given a vector, which is just a function on AB, and a real number, like lambda. Then the function lambda times f, defined on AB to real numbers, which to a point x assigns the number lambda f of x. This is again continuous. Okay, so I've given you the set and the two operations and pointed out that the set is closed under those two operations. We still need to check that this set with these operations satisfies all of the properties in the definition. So I'll let you check that. In particular, the distinguished element, the zero function, is just a function that assigns 0 to every point, the constant function 0. Okay, here's another example, also very important for this class. Okay, so curly M, subset M, comma n of f. This is how we're going to denote the set of all m by n matrices with entries in the field F. Okay, so this set is a vector space over F with, okay, so vector addition Okay, so here's how we do vector addition. So let's say that you give me a matrix A, and the way we're going to write this, so the matrix A, it's an m by n matrix, which means that it has entries A I1 through A M, and then down to A M1, and then over to A M N. Okay, so a much more compact way of writing this is to just we'll put square brackets, aij, and then here we'll say where I goes between 1 and m, and j goes between 1 and n. Okay, so if that's that's one of our vectors, which in this case are matrices. And then B is going to be the same thing. Now I'm going to just go straight to the compact form. Then A plus B is going to be the matrix whose entries are aij plus bij. So you just add entry by entry. Okay, and then that's vector addition, and then scalar multiplication. So given a matrix with entries aij and a scalar, let's say C, then C times the matrix is just multiply every entry by C. Okay, so notice that, so let's make this a remark. The vector spaces, so let's say R to the 4 and 2 by 2 matrices with entries in the real numbers, have elements, well, let's say have vectors that consist of 4 real numbers. And essentially the same vector operations, or vector space operations. Right, so if you, if I give you the vector 1, 2, 3, 4, and the vector 5, 6, 7, 8 in R4, or I give you the matrices 1, 2, 3, 4, and 5, 6, 7, 8 in the 2 by 2 matrices over the real numbers, then the vector addition is going to give you the next, well, another vector or another matrix, another column or another matrix, but you're going to have the same 4 numbers in either case. And same thing if I were to take one of these vectors 1, 2, 3, 4 and multiply it by 17, it's the same, I'm going to get the same 4 numbers as if I start with the matrix 1, 2, 3, 4 and then multiply that by 17. So this is a phenomenon that we'll talk more about later. Okay, there are more examples in the book. I strongly recommend that you read the section in the book to get more examples. Instead, let's now talk a little bit about the arithmetic. So just as when we talked about fields, and we noticed that the arithmetic in an arbitrary field is a lot like the arithmetic in the real numbers, same thing in vector spaces. The arithmetic in an arbitrary vector space is a lot like arithmetic in the real numbers, in Rn. So for example, additive inverses are unique. Okay, so let's check that. So if you have 2 vectors and they are both additive inverses of the vector v, then, okay, so additive inverse means that when I add it to the vector v, I will get the vector 0, right? And the vector 0 does nothing when you do addition, right? So what we could do is we could start with u1, right? And that's the same as u1 plus 0, right? But now what we could do is we could write 0 in a clever way. We could write 0 as v plus u2, right? And then we can use associativity of addition to say, well, that's the same as u1 plus v plus u2. And u1 plus v, because u1 is an additive inverse, that's just 0. So we get 0 plus u2, and that's u2. And that's what we wanted to check. u1 is equal to u2. Right? Here's another nice property that we're used to. Minus v is equal to v for all v. Right, so the same as saying, right, so this is really easy. You just need to unpack what you're saying. Okay, because remember, minus v is the vector that serves as an additive inverse for v. So it's defined by saying minus v is the vector that when I add it to v, I get 0. Right, so what is minus v? Well, it's the vector that when I add it to minus v, I get 0. Right? So we just need to notice that since both v and minus v are additive inverses of minus v. Right? And we just showed that additive inverses are unique. Right? So then they have to be equal. Right? And then here's another one that we're very used to, but until we prove it, you don't know this is true. And that is that minus v is the same vector you get by doing minus 1 times v. Okay, so again, think about the symbols. Minus v, that from the definition, that's the additive inverse of v. So what that means is this is a vector defined by the fact that if you add it to v, you get 0. Okay, and this is the scalar minus 1 in the field, right? So this is the additive inverse to 1 inside the field. And then here we're doing scalar multiplication, right? And the claim is that we get the same vector. Okay, so indeed, so just like a moment ago, we're going to check that these two are equal by seeing that they're both additive inverses to the same thing. So it is enough to check that minus 1 times v is the additive inverse of v. Okay. And we have, okay, so let's do it. Let's take minus 1 times v and add it to v, and we need to check that we get 0, right? But we already know directly from the definition that v, any v, is equal to 1 times v. So I can write this as minus 1v plus 1v. And then I can use the distributive property to write that as minus 1 plus 1 times v. And that's 0 times v, and that's 0. So that checks that. This is assuming that you've already shown that 0 times the vector v is the vector 0. I'll let you check that one. Okay, so to finish up, let's just notice that this simplifies checking that a subset is a subspace. Right? So we just need to check that 0 is in U and U is closed under vector addition and scalar multiplication. Right? The one we're leaving out now is closed under additive inverses, right? So we also had the fact that if you give me a vector in U, then minus that vector is in U, right? But now we know that if you're closed under scalar multiplication, then that includes being closed under additive inverses. Okay, perfect. So we will stop there for this lecture and pick it up from there next time.